var and wow hazards. Like for example here, we have R3 is equal to R3 into 5. Consider this as one instruction, another one, the third one. We had seen that there are these so-called anti-dependencies, true data dependencies, and output dependencies. And by renaming it appropriately, we could eliminate all these storage conflicts, that is, output dependencies and anti-dependencies could be eliminated. True data dependencies should not and cannot be eliminated because they represent the flow of information in the program, right? And we had seen that what the hardware does is to take any register that is available. Typically there is a large pool of so-called registers in a processor. In a modern processor, probably hundreds of them. So take a register that is available and put a tag or label it as some register. Like for example, here it is R3B and R3A. Why are these two not the same? Well, this R3 and this R3 refer to two different values, not the same value, right? This is a source value which is multiplied with R5 and you get this destination value. So they don't refer to the same value anyway. So they can actually be stored in two separate registers. And by using additional registers, we eliminate unnecessary dependencies. So here it's R3B, but this is the same R3B here. Because it's a true data dependency, so the information should be passed through one physical register. They are the same register. So the destination of this is the same as the source for this instruction. Now, here we have another copy of R3, which is R3C, and we can see that this R3 and this R3 are not the same because at this point, our purpose of this R3B, which is the original R3 here, is that it's no longer required because it was simply to pass the result of this operation to the next operation or the next instruction. So once the information is passed to the next instruction, this R3 is no longer required. It is freed up. Okay, so after this instruction has committed its result, the register R3B is released back to the original pool of registers. So you just mark it as no longer used. So the next time this original physical register that was storing R3B could be something like R5C or R5D. Okay, because all we do is tag an available physical register, and once the value is superseded and there are no outstanding references to it, it is essentially freed up and released back to the pool. So this is the idea of register renaming. And we saw that the whole idea of R0, R1, R2, etc. as corresponding to physical registers is no longer valid. The registers R0, R1, R2, etc. that you specify in the program is just a means for the programmer to pass information to the hardware. It does not necessarily correspond to a real physical hardware. Yeah. So registers that we write in our assembly language program are just abstractions, not really something which has a one-to-one physical counterpart. They are just abstractions to pass information from software to hardware regarding what is the data that is generated by an instruction and where it is used later on. Okay, so that is the idea of registers. So these so-called architectural registers are once again just abstractions. They need not, and generally in an out-of-order processor that supports register renaming, they do not correspond to physical counterparts or a fixed physical counterpart. Now we also saw this example where now using register renaming, you could actually rename these registers. Like for example, this R8 and this R8 is the same. By looking at the program order, the hardware is smart enough to realize that they refer to essentially the same value. But this one does not refer to the same value. Now that your purpose for R8 is done, you are just reusing R8 for something else, a totally different purpose, to store a totally different value. Right? So this R8 is different, and that allows you to rename, and that allows a better reordering of these instructions, which now is able to achieve your ideal IPC. For a 2-issue processor, the ideal IPC is 2. right? In every cycle, you have 2 useful instructions completing. So your IPC is now 2. So we achieved the ideal or the target through register renaming. Okay, so we saw superscalar processing where multiple instructions are started in a cycle. Then we saw that in an out of order processing you can rearrange those instructions. And in a processor which supports register renaming, we apply register renaming to expose more parallelism, that is to have rearrangements which were otherwise not possible. Yeah, so that is it. Now you have a better picture of how modern processors really work, right? Now let us look at the next topic, speculative execution, which is not an entirely new topic. We had seen one kind of speculation already, which is branch prediction. So modern processors speculate on a number of different things. Basically, without waiting for certain things to happen, we make assumptions, proceed with those assumptions, and at some point when we can cross-check and verify whether our assumptions are correct or not, we do the verification, and if our assumption was wrong, we undo whatever we did based on that guess, because our guess is now incorrect, right? We do damage control or rollback, or we won't commit the results based on speculative execution. So speculation is simply making guesses. And there are mainly 2 types of guesses that modern processors use. One guess is branch prediction, which we already saw in fair detail, right? Based on either a static prediction, that is based on a fixed policy that is fixed at compile time or design time, or a dynamic policy that is based on some sort of history. We make a guess regarding whether the branch will be taken or not. Okay, and then if the branch is predicted to be taken, we start fetching instructions from the branch target address rather than from the sequential stream that is immediately following the branch. Right? And later on, when we have the real result available, that is, once we realize whether the branch is to be taken or not, we check whether it matches with our original prediction. Okay, so at a point when you know that okay, the branch is taken, you then cross check. Did I predict that the branch is taken or not? And if you had predicted that the branch is taken and the branch is eventually taken, well, good for you. You did not even waste a single cycle waiting for the branch outcome. What if it is wrong? You have to basically undo the damage. So typically the results that are created by the speculative or speculated instructions are buffered rather than committed. You commit the result only when it is very clear that yes, those instructions were supposed to be executed. They were not in the wrong place at the wrong time. Then you commit the result. Now that is branch prediction, and some of you asked regarding the type of branch prediction used, etc., etc. And I did mention a few of them. Like one of the simplest form is using a 1-bit history, but there are multiple bit histories possible to per branch, which is the saturating counter approach. So whenever a branch is taken, you increment. Whenever the branch is not taken, you decrement. And if at a point when you make a guess, when you need to make a guess, if the count is past a certain threshold, you will predict that the branch is taken. If it is below the threshold, you predict that it won't be taken. Yeah, and it is a saturating counter, so it doesn't really keep counting. So if it is a 2-bit counter, it will count 0, 0, 0, 1, 1, 0, 1, 1 and stop at 1, 1. So it saturates at that point. Then there are other prediction schemes possible. This is a relatively simple prediction scheme, but still works fairly well, fairly hardware efficient, etc. But there are modern processors use more complicated information, like for example correlation between branches. If there are multiple branches in an instruction stream, there are typically correlations between various branches. There is typically a preferred path of execution in a typical program. Like for example, some branches are likely to be taken, some branches are not likely to be taken, because there is a preferred path of execution. So correlation between various branches rather than looking at the history of one single branch alone can actually improve your prediction accuracy. Okay, then there are also global trends. Okay, so the outcome of a group of branches is encoded as 1 or 2 bits or even more. So that is a global trend. So that global trend plus the local trend can actually improve the prediction accuracy over and above or better than just using the local information regarding one single branch. So modern processors do all these kind of interesting and intelligent techniques to make branch predictions. Okay, and it is still very much an evolving field. Like for example, the newer AMD processors, one of the main things that they claim is that their branch prediction accuracy is much better than the previous generation, which means people are still trying to improve it, which is partly aided by the fact that now you have a lot of transistors. More advanced prediction schemes naturally require more transistors. And now, since transistors are getting smaller and cheaper, you have more transistors available to do better prediction. Yeah? Oops.
Recording in progress.
When did that happen? Just now? Okay, lucky enough. Yeah. I think there is probably a network outage. Okay, so what I was saying is that now there are more transistors available. Transistors are getting smaller, and smaller means per unit cost of your transistor is getting cheaper, which allows manufacturers or chip designers to implement more advanced prediction techniques, which will require more hardware in terms of computations as well as storage. Like if you can store more history, you can typically get better prediction, right? So all these are made available because of XR transistors being available. So yeah, all these predictions are getting better and better. But these predictions also come with security issues. Okay, some of you might have heard about a couple of security issues that were quite or all over the news maybe 3 or 4 years ago. Spectre and meltdown. So that is related to speculative execution. So the speculative execution can cause information from one thread or one program to leak to another program. So a malicious program could actually gain information about a executing program by monitoring certain things like cache misses, etc. Okay, so speculative execution has its share of issues. So yeah, it's quite challenging to design all this stuff without running into those kind of issues. Another speculation that processors could use is what we call load speculation. Now let's look at these two instructions. So we have str, R1, let's say R2, and I have an LDR, let's say R1, R3, 8. Now can I rearrange these two instructions? Is it possible to rearrange these instructions? Not really, because you have one instruction writing to a register which is the source for a previous instruction. So you have some sort of a hazard, and this is called, what is this hazard called? Is it a true dependency or anti-dependency or output dependency? This is an anti-dependency, because if the two instructions are rearranged, str instruction will use the value of R1 created by LDR or returned by LDR, which is not how it should be, right? This R1 is an R1 returned by a previous instruction, and this R1 is returned for a following instruction. So if you swap the order, the meaning of the program has changed or will change, and that's not okay. So this is what we call an anti-dependency, where a following instruction writes to a register which is read by a preceding or a previous instruction. So you have an anti-dependency, which means that you cannot rearrange the instructions unless you do register renaming. So you could do register renaming. So for example, this could be, let's say, R1A, and this could be R1B, because they don't really refer to the same value. Okay. Okay, at this point, the original R1, this is R1A, was actually stored to the memory. Now, the purpose of R1 here was already served. R1 is freed up, and that's why we ended up using, as an assembly language programmer or compiler, we ended up using R1, or rather reusing R1. So they don't refer to the same value. We were just making use of available registers or reusing available registers. But now that we know that they don't refer to the same value, we could do renaming. And this renaming is done by the hardware at runtime in a superscalar processor. It's not visible to the programmer or the person who is monitoring the execution. It's a purely internal detail of the processor. Okay, how exactly it is done is up to the processor. It varies from design to design, manufacturer to manufacturer, and it is something the manufacturer wouldn't tell us explicitly because it is not something the programmer needs to know anyway. The programmer is guaranteed that the program will run correctly. How it runs is not the programmer's problem, right? So anyway, once you do a renaming, it is entirely possible to rearrange these two. Or is it? Okay, assume that you did register renaming. Now you no longer have this anti-dependency or war hazard. Okay, war hazard is completely eliminated. So that doesn't prevent you from rearranging anymore. Now, is there something that could prevent you from rearranging these two? Do you see any issues at all? What does this do? This writes something to the memory. This reads something from the memory. And it looks like the two memory addresses are different. So there is nothing wrong with rearranging, right? One instruction writes to one location, another instruction reads from another location, which are two completely independent events, provided the two addresses are different. Story will be complicated if R2 plus 4 is the same as R3 plus 8, which we don't know. Right? We don't know if R2 plus 4 is equal to R3 plus 8. If they are the same, we cannot rearrange because the store instruction has to write its result, which is read by the load instruction now, if they refer to the same memory location. So you cannot rearrange. In other words, we have to wait until store instruction has completed execution, or at least almost completed execution, before you know for sure whether we are referring to the same address or not, and only then can load instruction execute in fact. So a rearrangement without any checks is not okay, and this check is something which we cannot do in advance. The instructions have to execute, the ALU has to compute the effective address to even do a comparison. But then making a load instruction wait for long is not a very good idea, because a load instruction is not a very nice instruction for a hardware designer. It takes a lot of time, right? And things will be very, very bad if there is a cache miss. A load instruction with a cache miss can cause hundreds of cycles of delay. So there is definitely an incentive in being able to push load instructions ahead if possible. So what can we do here? Again, just make a guess that these two do not correspond to the same value. In other words, just make a guess that load and store refer to different address locations. So there is nothing stopping the load instruction from getting ahead of store, because load is going to read from a different location anyway. We don't have to wait for store to actually write it, right? So this is still a speculation. We don't know for sure. And whenever you do a speculation, you have the obligation to remember what you speculated and check later on when enough information is available to see whether your speculation was correct or not. And if it is not correct, undo whatever you did. All the results created out of speculatively executed instructions should be discarded. And we have to guarantee that any speculatively executed instruction does not change the machine state. It shouldn't accidentally modify a memory or a register or a flag. So everything has to be buffered until the speculation is cleared. Okay, so that's the idea. So there should be hardware and or software mechanisms to check and see whether the guess was correct. And we should have some mechanism to recover from the effect of instructions that were executed speculatively if your speculation or guess was incorrect. And these speculatively executed instructions can create exceptions, right? Possibly even based on wrong data because they were not supposed to be executed in the first place. So if there were exceptions, those exceptions should be buffered. Rather than treating it as a proper exception, we should buffer exception until the speculation is clear. Yeah? I mean, once you realize that, okay, your speculation was correct and there was still an exception, then treat it as an exception. Until that point, just buffer the exception. That's the idea. So that completes a discussion on superscalar processes, which are dynamic multiple issue processes, where all these decisions are taken by the hardware at runtime. Then there is a static version, where all the decisions regarding which instructions can be executed in parallel, the exact order of execution, etc., are taken by the compiler at compile time, which are what we call static multiple issue processes, which are also called VLIW processes. Why are they called VLIW? If, let's say, there are 4 instructions that are supposed to be executed in parallel, that are to be issued in parallel, what the compiler does is to create a bundle of 4 instructions. 4 instructions are bundled together.
You are muted on Zoom and you're not sharing screen.
Oh. Oh my god.
I don't know how long, but
Okay, thanks for letting me know. I think it is because of the disconnection. Oh, ouch, I lost quite a bit. Okay, never mind. Okay, so VLIW or dynamic multiple issue processes, static multiple issue processes, where the compiler packs independent instructions as a bundle, and the bundle can be thought of as one long instruction, and hence the name. Okay, so let's say if there are 4 instructions that are supposed to be executed together, the compiler creates a bundle of 4 instructions, and that looks like one big instruction. In reality, there are 4 separate operations bundled up together, and hence the name VLIW. The compiler is responsible for almost everything. Okay, dependency check, bundling up together, etc. And the compiler also does loop unrolling to expose more ILP. What is loop unrolling? Let's say if I have I have a code, higher level language code. For example, for I is equal to 0, I less than let's say 4, I plus plus, and then let's say A of I, is equal to B of I plus 1. Now, this is essentially just incrementing the elements, adding 1 to the elements of one array and storing it into another array. Can it be done without using a loop? Yes, you could always write something like, say, A of 0 is equal to B of 0 plus 1, A of 1 is equal to B of 1 plus 1, etc. A of 3 is equal to B of 3 plus 1. Now here everything is very, very sequential, right? You have to do an addition, then do an incrementation of I, check whether I is less than 4, if not, go back to the beginning of the loop. So everything is very, very sequential. There isn't much scope of executing things in parallel. Whereas here you see, now we split it up or unrolled it into practically 4 separate operations, which can in some sense be done in parallel or in any order. So now we are exposing more instruction level parallelisms. Yeah. So yeah, compiler does this, and is there any positive? Yes, of course. You can now schedule things at compile time more effectively, right? And the compiler can actually bundle all four of them possibly into the same bundle if it is a 4-issue processor. Because all four of them can technically be run in parallel. There is no dependencies between them at all, right? Of course, you could run to structural issues related to array or memory accesses, etc. But otherwise, from a data perspective or a control perspective, there are no dependencies at all. So you could actually bundle them together because now we expose more ILP. What is the flip side? Nothing comes free, right? So what is the price we are paying? Now your program size becomes big. Okay, here it was only 4 iterations, so it's not so bad. But what if you had like 16? Then something which look quite compact will look very long in the unrolled code. So your binary size will become quite big. Your code will become quite bloated. So that is a negative side. But it exposes more ILP, it can run, or it will almost certainly run faster. Not almost certainly, it will certainly run faster than this. Yeah? So now you see, there is a trade-off between program size and program speed. And this is a typical trade-off that you can control by controlling your compiler appropriately. Not just for VLAW, for any processor. In fact, if you go to compiler options, there will be settings to optimize for speed, optimize for size, etc. And they are usually mutually exclusive or rather conflicting requirements. Okay, if you try to increase the speed, you will typically end up with bigger code, bigger executable size. And then the compiler will do more aggressive unrolling and stuff like that. Okay, and in VLAW processes, the compiler is more or less obliged to do a lot of unrolling and stuff. Otherwise, it can't expose any parallelism at compile time. And it does compile time register renaming rather than runtime renaming. That is, register renaming is done using visible register set. So there is no R3A, R3B, etc., which are internal to the processor. Now there are more registers that are visible to the programmer. Okay, many VLAW processors have something like 128 registers visible to the programmer. So you can write like R1, R2, R3, R65, R79, etc. But what is the disadvantage of having a visible register set that is very big? Again, the instruction length will increase because to denote or to identify one register, if you have 128 registers, you require 7 bits. And in any and almost every instruction will have 3 registers specified. And the 3 registers alone will take up 21 bits, as opposed to 12 bits in the original ARM processor. Right? And that also increases your instruction word length. Okay, which also partly is the reason why it is called VLAW. Your instruction word length increases. Now, while superscalars use dynamic prediction, VLAWs primarily depend on compiler for everything, including branch prediction. Often, the compiler will do the prediction and encode the prediction as a hint bit in the instruction format. We did discuss about hint bits, right? Yeah. And it will do loop unrolling to reduce the number of branches altogether. So by unrolling loop, we are reducing control dependencies. And it also typically does a lot of predicated execution, or simply called conditional execution. So a certain instruction is done using or attached with a predicate. Like for example, you can have something like say and EQ or sub NE, etc. So this kind of conditional execution can reduce the number of branches that you will have in your program. Okay, which reduces the need to do any kind of branch prediction, etc. Okay, and branch prediction is pretty difficult to do at compile time properly anyway. So VLAWs heavily depend on eliminating the need for branches wherever possible. So some of these are techniques whereby branches can be eliminated or reduced. Now, classic example for VLAW is Intel Itanium. When I was in college, Intel Itanium was said to be a very big thing, the thing of the future. Okay, it was all over tech websites, etc. The idea was that Intel, in early 2000s, it was very clear that 32-bit computing will not be sustainable. That is, 32-bit computing alone cannot meet the requirements of many modern applications, where the address space, the data size, etc. can be bigger than what a 32-bit computing or computer can offer you. So the transition to 64-bit was inevitable, and two competitors, Intel and AMD, took radically different approaches to moving towards 64-bit computing. Intel decided that it's time for a change. So they designed this radically different VLAW architecture called Intel Itanium. Okay, they named it EPIC, Explicit Parallel Instruction Computer, which is VLAW plus some modifications or some I would say advantages over a standard VLAW. Okay, I'll talk about that later. But fundamentally, it was a VLAW architecture. And Intel collaborated with HP, which was and still is a big name in server market. And their idea was that initially the 64-bit computing using Itanium will be introduced in server market. And gradually it will percolate to the user space, that is for consumer space, for consumers. So the vision was that eventually the Intel x86 architecture will be replaced by IA64 architecture. Now, EPIC or Intel Itanium had 128-bit bundles consisting of 3 instructions or operations. So it was a 3-instruction bundle. Each instruction is 41 bits plus a 5-bit template field explicitly specifying which functional unit each instruction needs. So the functional unit required by an instruction was very explicitly specified in the instruction itself, which meant decoding was very simple. You could read a certain field and straight away know which functional unit should execute that particular instruction. So if it is an integer instruction, it could be straight away dispatched to the integer unit. And if it is floating point, it could be sent to floating point unit without the need for much decoding or front-end circuitry. There were 5 functional units: integer ALU, multimedia, data memory, floating point ALU, and branch. There were 128 integer registers and 128 floating point registers. And floating point registers were 82-bit long to preserve precision for intermediate results. So double precision floating point requires only 64 bits, right? But intermediate results can be bigger, and if there are wider registers for storing intermediate values, you can avoid the need to do unnecessary rounding at each step, which means your results can be more precise than it could be if you stick to, let's say, 64-bit grid. Okay, and this is fairly common in a lot of custom hardware, where even though your data size is, let's say, n bit, the interim results are usually stored using much more than n bits, so that the precision can be preserved and the need for rounding is avoided at intermediate steps. At some point later, when you eventually write the result to a user accessible register or visible register, it still has to be rounded. But in between, they can avoid rounding. But here, even user accessible registers were actually wider to allow for better precision. It had extensive support for speculation and predication. Intel hoped, I just mentioned, that it will take off in the server market and later percolate to the PC or consumer market. Now, AMD, Intel's competitor, took a very radically non-radical approach, which is just to extend the 32-bit instruction set to include 64-bit instructions, which meant that all the current programs ran without any modification whatsoever. But programs which were compiled for 64-bit architecture were able to make use of bigger registers, bigger numbers and memory sizes, etc. Okay, so existing program ran without any modification whatsoever. Now, no prices for guessing which one was eventually successful. We use 64-bit computers now, and even Intel 64-bit computers actually make use of that extension done by AMD. Okay, so AMD as a company started off by copying Intel, and it was Intel's chance to return the favor. Okay, so they called it EM64T, which was nothing but AMD's modification or enhancement to the 32-bit instruction set to make it 64-bit. And that's why operating systems or platforms like Linux still calls it AMD 64. Okay, even Intel processors with 64-bit is still called AMD 64. Now, there were a few problems with Titanium. Number one problem was that, well, some things are too good to be true, right? So they were hoping too much from the architecture. The idea was very good, but Intel couldn't come up with a compiler which was compelling enough for people to adopt it. That is one reason. The other reason is that industry generally doesn't like change. Nobody wants to take responsibility, right? And compiling to a new platform would mean that you have to ensure that everything is okay, security is good, etc., in the new platform. And people naturally did not want to do that. Industry many a times follows a policy that if it is not broken, don't fix it. Yeah. So unless there was a compelling reason, there was no motivation to change, and actually not many people or not many companies moved to 64-bit or basically IS64. Not to be confused with x86-64 or AMD 64, which is what I just mentioned, AMD's extension of the original 32-bit instruction set. Now, what are the advantages of VLAW? Simpler hardware. A lot of work is done at compile time by the compiler. So the hardware is a lot simpler, especially the hardware front end, which have to or has to do decoding, possible rearrangement, etc., is now a lot simpler because most of the dirty work is already done for the hardware. Potentially more scalable. You can simply allow more instructions per bundle and more functional units. Simply by adding more functional units and more instructions per bundle, you can actually improve your throughput. And since every check is pretty much done at compile time, there isn't much of an increase in complexity in the hardware which is supposed to do all these checks, because most of the checks are already done at compile time. Superscalers are not so scalable because when you are adding more and more or when you are increasing your issue width, you need a lot more hardware to do all these dependency checks, rearrangements, etc., etc. Things don't really scale that well. Whereas VLAWs are at least theoretically a lot more scalable. Now, disadvantages: programmer complexity and longer compilation times. You know, writing an assembly language program for Intel Titanium is next to impossible. It's not meant to be written by humans, right? Automation was essential because it was complicated. Not all stalls are predictable, so there is a limit to how much the compiler can make predictions at compile time. Okay, a lot of predictions require runtime information. Okay, like for example, if you need to know what is a past trend of branches, whether they were taken or not, you need to have history, runtime history, which cannot be obtained at compile time. At best, what you can do is do some kind of profiling using some example data at compile time. But that is again not very representative of the real world dynamic data that the processor might need to execute or deal with. So branch outcome was, or many a times is dynamically determined, so it is very hard to make predictions. The other problem is object code incompatibility. So the code that is compiled for one specific microarchitecture may not be compatible with another microarchitecture. So microarchitecture dependence. Now the good news about EPIC, Intel's implementation of VLAW, was that the program compiled for one microarchitecture will work correctly on another microarchitecture. So the correctness was guaranteed by hardware. I forgot to mention it on the slide. Correctness was guaranteed by hardware, but performance is not. So whenever the hardware feels like, okay, the code does not really match the pipeline structure, it will simply stall the pipeline and ensure correctness of execution. But if the code is compiled with the correct pipeline structure in mind, it will run optimally or efficiently. Okay? So recompilation to meet or to align with the new microarchitecture is necessary to obtain good performance, but correctness does not require a recompilation. Okay, so that was one positive thing about Epic. But the performance when the software did not match the hardware was pretty bad. Okay, and that is one of the reasons again why industry did not like it too much. And it requires a lot of program memory bandwidth and a lot of code block, because all these compile time stuff requires your loop to be unrolled, etc., etc. So all this require a lot of program memory bandwidth. And if the compiler cannot find independent bundles of the certain n number of instructions, it has to part the rest of the instructions with NOPs. And all this will add to your code memory size as well as program bandwidth requirement, program memory bandwidth requirements. So because of all these reasons, VLAWs did not become very popular in the CPU space. It doesn't mean VLAW was a technology which never took off. It is still widely used in relatively special purpose processors. For example, GPUs. Okay, certain AMD GPUs, certain family of AMD GPUs, I can't remember exactly which family, makes use of VLAW processing. Okay, where instructions are bundled together. And most or many digital signal processors, array processors, etc., also do VLAW style processing. And you can see all these digital signal processors, GPUs, etc., they typically deal with a lot of massively parallel data, where the focus is typically more on data processing rather than controls. Like there typically aren't too many branches, etc., when it comes to signal processing. Okay? In such cases, compile time bundling up can be done more efficiently than it is for general purpose computing. And that's why for general purpose computing, VLAWs are not popular, but for specialized processors like GPUs, DSPs, etc., they are popular and widely used. Okay, some of the Texas Instruments digital signal processors do use VLAW. Okay, TMS some 3 something series, I can recall exactly. Now, does multiple issue work? Yes, but not as much as we would like. Programs have real dependencies that limit ILP. Some dependencies are hard to eliminate, some parallelism is hard to expose. Especially for superscalar processors, in order to do rearrangement, they have to look at a window of code, and that window can't be very big. And if your window is not very big, you will miss out possibilities to parallelize things. Only those within the window can be rearranged, right? So that's again a problem. And again, even if the processor is fast, memory might not really catch up. So it may be hard to keep pipelines full. And speculation can help if done well. Like for example, using load speculation, you can hide a cache miss penalty to some extent. Yeah. Okay, so that is about it for multiple issue processors. Now let us look at multi-threaded processors. The next 2-3 slides are something which those who have taken a course on operating systems will be familiar with, either CS2106 or CG3207. A process is a program that is running on a computer. A program is a binary code that is stored in a storage, like for example hard drive. When it is loaded for execution, it's called a process. And a thread is typically a part of a program or a process. one process could be composed of multiple threads. Like for example, winword.exe, if you are using Windows. That is a process associated with the program Microsoft Word, right? But it has multiple more or less parallel streams of execution within it, and they are called threads. Like for example, a word processor could have one thread to deal with keyboard inputs, another thread to do spell checking, another thread which could be doing printing, etc. So these are relatively parallel streams of execution which share a memory space and do interact with each other typically through a shared memory or a common memory space or so-called page table. So they have all the threads within a process have the same page table. The operating system can schedule threads. So decision on when and for how long a thread can run is taken by the operating system. In a conventional processor, only one thread can run at any given time. Okay, at any given instant, only one thread will be running in a conventional processor. Whereas in a multi-core or multi-processor system, the number of threads running is equal to the number of cores available. So in a 4-core processor, 4 threads can be running truly in parallel, that is at the same time. But in a single-threaded processor too, the operating system will switch between threads fast enough that the user gets the illusion that these multiple threads are running in parallel. When in reality they are not running in parallel, they are running in a time-sliced manner, in a time division multiplex manner. That is, one thread will run for some period, some amount of time, then it gets suspended, then another thread gets to run, and so on. But if the switching between threads is fast enough, the user gets the illusion that all these threads are running in parallel. Now, in cooperative multitasking, the operating system will have to wait for one thread to stall. So the operating system allows one thread to run, and that thread runs until it stalls. And a thread stalling means either it calls a certain delay function or it requests the operating system to read or write an input-output device, etc. So when a thread requests the operating system to do something for it, the thread is essentially said to be stalled or blocked. So when a thread is blocked, the architectural state of that thread is stored. The architectural state of the waiting thread is loaded into the processor and it runs. And what do you mean by architectural state? Basically all the registers and other necessary information that a program requires to run. So this is called context switching. So you are essentially suspending one thread when it requires some service from you, so that is when it cannot run anymore, and then you switch to another thread which is ready to run. And this process is called context switching, and the operating system scheduler, based on the various scheduling policies used by the operating systems that are in question, will decide which thread is to be run next. Yeah? And there are a lot of different scheduling algorithms, like for example, round robin will give more or less equal time for each thread. There are priority based scheduling, where the priority itself can be dependent on various factors such as the frequency of the task arrival or when the deadline is, etc., etc. Yeah. So anyway, the decision on which one is to be run next is taken by the scheduler. So in cooperative multitasking, the OS has to wait for one thread to stall before it can switch to another thread. Whereas in preemptive multitasking, the context switch can also be initiated by the timer interrupt and not necessarily when one thread stalls. So before the control is given to a particular thread, the operating system will set a timer. And once the timer times out, it will generate an interrupt, and the interrupt handler is considered to be a part of the operating system. So OS gets back control or receives back control from the currently running thread. And then the OS gets to choose whether to allow the current thread to continue or to switch to another thread. Okay, so that is preemptive multitasking, and almost all modern operating systems are preemptive multitasking operating systems. Okay, even though macOS, the older versions, did have some element of cooperative multitasking. And real-time operating systems which need to give time guarantees are almost exclusively preemptive multitasking operating systems. Now, similar switching can be done by the hardware too, without the operating system initiating a context switch. So in hardware multithreading, the processor maintains multiple copies of architectural state. So for example, it could have multiple copies. So even though there is, let's say, only one processor core, the software facing side could be duplicated. For example, all the registers R0, R1, etc., the program status register, the page table base register, etc., are all duplicated. So the operating system sees it as multiple cores. So even though it's in reality only, let's say, a single core processor, because there are two separate architectural states, it will be visible to the software or operating system as two different cores. And when there are two different cores, the operating system will schedule two different threads. Now the switching between the threads will be done by the hardware based on various policies. So now the context switch is in some sense performed by the hardware. So when one thread stalls for minor events such as cache misses, the other waiting thread can run immediately without the operating system initiating a context switch. So something like a cache miss can have a penalty of a few hundreds of cycles, okay, which is not major enough for the operating system to switch threads or come in and switch threads. In fact, if the operating system comes in and switches threads, that itself will most likely cause a cache miss. Okay, so there is absolutely no point in invoking the operating system for minor events like cache misses. So then the hardware can do the switching, and hardware can do the switching in a matter of a cycle or a handful of cycles, thereby not wasting most of the cycles. So this is called coarse-grained multithreading. Now, multi-threaded processing does not improve the instruction level parallelism of a single thread. So the speed of execution of a single thread does not increase, but the overall throughput, the overall work done by the system increases by eliminating unnecessary waits in between, like for minor events. So multi-threaded processors exploit thread level parallelism rather than instruction level parallelism. Instruction level parallelism is within a single instruction stream or within a single thread, whereas thread level parallelism is the amount of independence and the possibility of two threads or two independent streams of execution being executed in a concurrent manner. That is, without waiting for one to finish, the other one can run because the two of them are more or less parallel or more or less independent. Not parallel, independent. Now, there is fine-grained multithreading, which, unlike coarse-grained multithreading, switches between threads every cycle. So, in one cycle, you will have thread A in an instruction from thread A going in. In the next cycle, you have instruction or instructions from thread B going in. So thread A and thread B sort of runs in alternation. So thread A and thread B are in some sense running in a round robin fashion. Okay, at a very, very microscopic or a very fine-grained level, usually at the level of every clock cycle. So every clock cycle there is a switch. What is the advantage? It spaces instructions from a single thread by at least one instruction. So for example, if the instruction from thread A goes into fetch stage, the immediately preceding instruction will not be in decode stage, it will actually be in execute stage with a one instruction gap in between, and that gap instruction is from another thread. which essentially means that the instruction in between is independent of the two instructions that are on either sides of it. And that reduces your dependencies, the number of instructions with dependencies within the processor, as well as misprediction penalties. So if there is a misprediction, you need to flush only those instructions from the thread which had a misprediction. Others need not be affected, right? So this is called fine-grained multi-threading, and a processor which performs fine-grained multi-threading is called a barrel processor. Okay, not very popular, but such processors have been designed historically. Now, the last hardware multi-threading model is simultaneous multi-threading. Okay, where unlike the two previous cases, coarse-grained and fine-grained, the alternation between threads is not strictly temporal. In the two previous cases, it's strictly temporal. Only one or the other executes. Right? At least in one particular clock cycle, you issue instruction from one thread or the other thread. So they run in some sort of a time shared manner. Whereas in simultaneous multi-threading, it is possible for the processor to issue two different instructions from two different threads in the same cycle. So if one thread can't keep all execution units busy, another thread can use them. For example, if one thread does a lot of floating point operations, another thread does a lot of integer operations. By issuing instructions from both threads at the same time, you can maximize the available computational power within the processor. You know, the mainly integer thread will be using only those integer units. And if we did not have instructions to use floating point units, those floating point units would be sitting idle, right? And a costly resource sitting idle is underutilizing it. So you could issue instructions from another thread which could actually make use of those units. So that is simultaneous multi-threading. So instructions from different threads execute at the same time. So you can achieve good performance or make use of the existing computational units well. That is, you can achieve better performance without duplication of functional units. So it has both spatial and temporal aspects. You know, there is some spatial as well as temporal aspects to simultaneous multi-threading. Spatial means, you know, from different threads. Temporal means at different times. So there are aspects of alternation with respect to time as well as with respect to space. Okay, whereas the previous two, that is coarse-grained and fine-grained, are purely temporal. There is no spatial alternation or parallelism involved. Now, Intel clients, they could achieve like 25% improvement in performance. And when we talk about performance, we are talking about throughput, not the performance of a single thread, which doesn't increase, but the overall work done could increase by up to 25% with only 5% extra hardware. So it requires some extra hardware because now each instruction should be tagged properly to specify which thread it belongs to. And whenever you do any kind of dependency check, you need to do dependency check only between instructions from the same thread. Right? But all this additional tagging, etc., requires additional hardware and intelligence, and that's why it requires extra hardware. But that extra hardware is probably more than worth it in terms of the throughput improvement that you get. Okay, but of course, terms and conditions apply. Operating system needs to be SMT aware. By the way, SMT is known in Intel terminology as hyperthreading. Intel uses the term hyperthreading, and Intel processors were capable of hyperthreading for quite some time. Okay, and almost every Intel processor that you are using is actually using hyperthreading. It has been around from mid 2000s, that is from the age of Pentium 4. Okay, whereas AMD managed to do it only recently, in the last, I think about 4 years ago, with their Zen processors, Zen series microarchitecture. Okay, so that is hardware multi-threading. And with this, we are ending this chapter. But it's not the end of the story yet, because we will continue in the next chapter and talk about multiprocessor systems. Okay, but before that, well, let's take a break for about 13 minutes. Come back here by 7:15, okay, so that we can have all of this. The product of two n-bit unsigned numbers can be always expressed using n bits, whereas for signed numbers, it might need up to 2 n bits. Is it true? No. For both signed and unsigned, if you multiply an n-bit number by an n-bit number, you might require up to m plus n bits. Okay, which follows the principle that x raised to m into x raised to n is x raised to m plus n, right? And here x just happens to be 2 because your x is 2. Okay, so same principle here. It can be up to m plus n bits. So in general, for n bit plus n bit, sorry, n bit into n bit, you might require up to 2 n bits. Okay, some of you might have been confused because in the sample multiplier that was given in lab, it required twice the number of clock cycles for sign multiplication, simply because it was implemented kind of inefficiently. Yeah? Not because the number of bits in the results are different. But one point to note here is, out of the 2n bits, the first n bits could be different for signed and unsigned. The last or least significant n bits are the same irrespective of whether it is signed or unsigned. And if your numbers are small enough that your result can be contained within n bits, then the result is the same for signed and unsigned. Okay, but if your result is supposedly bigger, that is if the numbers are bigger, then the results are different for signed and unsigned, but in either case, you may require up to 2 n bits. Now, represent the number minus 9.875 in single precision floating point format. So, minus 9.875, right? This is 1001. Forget about the sign, because in floating point system, sign is accommodated using a separate bit. Okay, so when you do the encoding for the rest of the bits, whether it is negative or positive, it's the same. All 31 bits are the same, only the most significant bit is different depending on whether it is signed or unsigned. So 1001.875 is 0.5 plus 0.25 plus 0.125, okay, which is 111, which is 1.001111 into 2 raised to 3. Okay, now when we encode it, the first bit is sign bit, which is 1, because the sign is negative. Then the exponent field is the actual exponent plus bias, which is 127 plus 3, which is 130. 130 is 128 plus 2, which is 1 followed by 7 zeros plus 1 0. So 1 followed by 7 zeros plus 1 0. So this will simply be 1. And the rest of the bits are these bits. Okay, the bits after the point, which is 0 0 1 1 1 1. Now in hexadecimal, this will be 1 1 0 0, which is C. 0 0 0 1, which is 1. 0 0 0 1, which is 1. And here it's all zeros. So 1 1 1 0, which is E, and the rest are all zeros. So C 1 1 E. So hexadecimal C 1 1 E 0 0 0 0. Yeah. Now, yes. Zero. Oh, 0x. Oh, no, don't worry. Okay, this part is also fine. Yeah? Now, provide an expression for overflow in subtraction. When we have an overflow, In addition, you have an overflow when you add a positive number with a positive number and you get a negative number, or negative number plus negative number giving a positive number. This is for addition. But for subtraction, the story is a bit different. Positive minus negative giving you negative is not good, right? Because positive minus negative should be even more positive. So if you get negative, it's because your results are catastrophically wrong. Or a negative minus positive should be even more negative, but if you get a positive, it's bad news. So these are the two situations where you have an overflow in subtraction, which essentially means that you need to have the two numbers of different signs. And how do you check that part? Yeah, using XOR. You can have A31 XOR B31 to ensure that they are of different signs. Now, the result should have a sign which is a same as the second operand, which is different from the first operand. Okay, so you can do it either way. You can either write A31 XOR S31, or it's also okay to write B31 XNOR X31. Either of them is okay for the second part. The first part has to be this. The second part can be either this or this. Of course, connected using AND. Yeah. Well, as long as your logic is correct, it's okay. Yeah, it doesn't matter whether you write it as XOR like this or if you use XOR notation like this. Okay, now next question. Executing the following instructions, LDR R4, R2 each, and STR R3, R4.
It shouldn't be from M to E though.
This is a standard load and use scenario. Okay, where R4 writes to a register which acts as a source register for the instruction that follows it. A very standard load and use scenario. And a standard load and use scenario, what happens? There has to be a stall. And it has to be followed by a forwarding which is from. What is a stall for? To insert a gap or a one cycle separation between LDR and the following instruction. And then you have your W to E forwarding which will take care of delivering the correct data. Okay, so you have a stall, you have a W to E forwarding. These can't be the case because the forwarding is between two units which are next to each other. Okay, forwarding should be in such a way that there is a one gap, one cycle or one stage gap between the two. So it is W to E forwarding. Now, if a branch decision is committed in W stage, it is essential to ensure that the instruction in M stage is not a store. Because if your branch is committed in the last stage, the immediately preceding instruction, which is the instruction that follows it, for example, in a 5-stage pipeline, okay, this is D, E, M, W. So if you have a branch here and if you have a store here, by the time the branch commits the result, the store would have already returned to the memory. So what if the branch instruction was not supposed to be, branch was supposed to be taken, not supposed to be, supposed to be. So if the branch is taken, the immediately following instruction should not be entering the pipeline in the first place, right? And now you have a scenario where the store instruction enters the pipeline and has committed the result to the data memory. So it's already too late, the damage is already done. So in such a scenario, what should you do? What if you have a scenario where you have a store instruction immediately following a branch? You have to store. Okay, the way you store is exactly the same way you store for load and use case. When branch instruction is in the execute stage and str instruction is in the decode stage, you can already sense that this problem is going to happen. And then store your store instruction so that you insert a one cycle gap between your branch instruction and store instruction. So by the time your branch instruction reaches write back stage, your store instruction will only reach execute stage. And it getting discarded after reaching execute stage is okay, but it getting discarded after reaching memory stage is not okay, because memory stage is a stage in which your store instruction writes something. Okay, and by the time you realize that store instruction was not supposed to be there, it will be too late if they don't have a gap between them. And it's not just the store instruction that has a gap or that has this problem. There is another instruction which will have this problem. Which one is it? And that problem is even more severe. Any instruction that writes to the flags. Okay, for example, a CMP instruction. CMP instruction would already be in memory stage, which means it has already returned to the flags one cycle ago. By the time you realize that, well, the RAM is taken, it's already too late, the damage is done. Okay, so in these two cases, you have to recognize the problem and insert stalls appropriately, which can be done when the second instruction reaches decode stage. That is the earliest opportunity for you to realize the nature of the instruction, right? And then you can insert stalls. And inserting stall is done pretty much the same way as inserting stall for a load and use case. Okay, but to put it simply, the answer here is stall. Okay, so that is it, folks. But we are not done with the lecture yet. If you have any urgent business to do which is more important than the lecture, please go ahead. Okay, otherwise stay back. Systems. Okay, in fact, that is probably the last part with respect to how to make the processor faster. Okay, the rest of the chapter is about exception handling as well as input-output handling in a rather great manner. Yeah. So let us look at multiprocessor systems. But before that, let us look at the various categories of computers. Okay, there is the so-called Flint's taxonomy. Okay, which is not entirely representative of every possible scenario, but this is a classic categorization that we have used historically. People still use it, even though many modern computers fall somewhere in between. There are 4 categories according to Flint's taxonomy: SISD, SIMD, MISD, and MIMD. SISD is your standard single threaded processor. Okay, even if it is multiple issue processor, it is still operating on a single thread using a single stream of instructions and data. So that is called SISD. A sequential computer which exploits no parallelism in the instruction or data stream. Traditional uniprocessor machines, even those uniprocessor machines which are multiple issue are still SISD processors. Yep, they do make use of instruction level parallelism, but nothing beyond that. But it is still operating on a single instruction stream, so SISD. Then we have SIMD, a very popular paradigm: single instruction, multiple data. A computer that exploits multiple data streams against a single instruction stream to perform operations which may be naturally parallelized. Let's go back to the example that I had given earlier after loop and while. You had stuff like A of 0 is equal to B of 0 plus 1, all the way to A of 3 is equal to B of 3 plus 1. Right? So we had essentially 4 operations which are actually the same operation done on 4 different data points. Right? So it's essentially the same set of operations, or in some sense the same instruction stream applied to 4 different data streams or 4 different data points. That is called SIMD. It exploits a parallelism that we did not talk about so far, data parallelism. The fact that all these data points can be independently operated on is essentially your data parallelism. The nature of the data in such a way that each data point is independent of the other. And as you can imagine, this happens quite a lot in real life. A lot in signal processing, image processing, video processing, machine learning, etc. Okay, where you are operating on different data points, and they can all be operated on in parallel. Okay, the most classic example would be, let's say, image processing or graphics, computer graphics. Now, if let's say you need to rotate an image, okay, there is this image that needs to be rotated by an arbitrary angle. How will you do it? The position of the new point or the position of the corresponding point in the rotated image needs to be calculated for each point. Take each point and find its location in the rotated image. And that is done using or by multiplying the coordinates of this point by a certain rotation vector. Right? Something like, say, cos theta, sin theta, minus sin theta, cos theta or something. Okay, I can't recall whether the sign is here or here, one of the 2 different places. So, if you want to apply a rotation by theta, you take the xy coordinates of the original point and multiply it by this matrix. And then you get the new location or the new coordinate x dash y dash in the rotated image for that particular point. And this has to be done independently for each point. Right? So if you have, let's say, an image which is 1024 by 768, and if you have a processor, a hypothetical processor which can deal with about 1 million points at the same time, you could do this operation on all the 1 million points at the same time. Because each point is independent of the other, right? At least for this example. So you are essentially having massive parallelism with respect to how the data is supposed to be processed. So you have data parallelism. Example for processes that make use of this data parallelism are array processors and graphics processing unit. And in fact, most hardware accelerators make use of data parallelism. Okay, most of these so-called tensor processing units or neural processors, digital signal processors, digital image processors, almost all of them are fundamentally SIMD type processors. Any guess how much processing units are there in a modern graphics processor? Like for example, NVIDIA 3090 Ti. Any guess how many processing units are there? More than 10,000. So it's a massive amount of parallelism of hardware or parallelism in hardware. So if your data is in such a way that it can be operated on in parallel, you can deal with like 10,000 data points at the same time. Whereas a conventional processor will deal with only 1 data point at a time, assuming a single processor system. Even with an 8-core system, you can probably deal with 8 data points. And a CPU deals with each data point faster than a GPU. Okay, but even an 8-core processor, even if it executes like 10 times faster, will only be having the effect of an 80-core GPU. And modern GPUs have much more number of cores. Even the lowest end GPU that you can buy from the market can or will be able to operate on probably about 1,000 data points at a time, or probably a bit less. 500 to 1,000 is a typical range for a integrated GPU. Okay, now MISD, which is a rather uncommon architecture where you have multiple instructions that operate on a single data stream. So you have a data stream that is coming in and you are performing parallel independent computations or independent instructions being applied to the same data. It is not very common. It is generally used for fault tolerance, like autopilot systems and control systems that deal with safety critical systems. Yeah. Airplane autopilots almost always have some MISD kind of processing, where the same data is processed by different computers, and then they compare their result to see if they tally. Okay, possibly using different algorithms, etc. And if their results don't agree, it's an indication of a problem. And in many cases, autopilot will disconnect and will give a warning to the pilot. Okay, so sorry, I can't deal with this anymore. I leave it to you.
Broken also.
Okay, it happens when, for example, the results disagree. This could be because of some fault in one of the computers, etc. Now,
Previous one completely cannot.
multiple instruction streams and multiple data streams, where you have multiple autonomous processes simultaneously executing different instructions on different data. And this is the case with most multiprocessor systems. Parallel and distributed systems, either they use shared memory or distributed memory. So basically, there are independent processing units which work on different instructions and different data. And they make use of thread level parallelism, where each processor could be operating on a separate stream of instructions or a separate thread and separate data. Okay, but the overall throughput of your system is enhanced because you are doing more things at the same time. So that is the classic scenario of multiprocessor systems. Now there are two categories of multiprocessor systems. But before we get there, let us look at what is the motivation for multiprocessor systems. You know, most desktop processors that were released about 12-13 years ago were single processor. But almost everything that was released over the last maybe 13 years are invariably multiprocessor systems. On mobile phones, or portable devices, it came a bit later, but again, probably for the past maybe 8-9 years, it has been mostly multi-core systems. Now, what motivated this switch towards multi-core or multiprocessor systems? Diminishing returns with your attempts to improve the performance of a single thread or a single stream of instructions. We already saw a few reasons for that. One way to increase the performance of the system is to increase the clock frequency. But we saw that we have diminishing returns. Okay, the same goes for any attempt to increase the number of instructions that are issued in parallel, like issue width. Practically, you don't have processors having issue width of more than 8. Okay, and vast majority of processors use something like 4. So any attempt to bring it above 4 has diminishing returns, and above 8 vastly diminishing returns. Probably not worth your time and effort. Okay, because real life threads do not have that much amount of parallelism, ILP, that you can exploit, right? And that limits your available performance enhancement. So that is your ILP goal. Increasing difficulty to find enough parallelism in a single instruction stream to keep a high performance single core processor busy. Another issue is memory wall, the increasing gap between processor and memory speeds. Okay, for single processor systems, you will have essentially one window or one channel through which you access memory. And that channel or that processor to memory link many times can act as a bottleneck. Then power wall. Whenever you attempt to improve the performance in almost any manner, you compromise on power. Right? For example, if you try to increase the clock frequency, you have to increase the pipeline depth, and again operating frequency directly impacts your power. Remember your power equation? Power is proportional to C V square F. C is capacitance. V square, of course, voltage, and this is a frequency. So a transistor which is switching faster will require more power. The voltage swing will also determine or will affect the power very significantly. And also the capacitance. Capacitance is usually related to the process technology as well as the number of transistors a particular transistor drives. Okay, so all this adds to the power. Okay, and in fact there is some relation between voltage and frequency as well. In order to get higher frequencies, you typically need to increase the voltages as well. Okay, so that you can charge and discharge these capacitors faster. Okay, so in fact the relation between voltage and frequency is a bit more complicated. So increase in frequency means you typically have to increase the voltage too, and that increases your power requirement quite tremendously. Okay, so it poses manufacturing, system design and deployment problems. So it's not just about the electricity bill, it's also about the requirement to dissipate this power, which will require heat sinks and other cooling mechanisms, fans, etc. to dissipate the heat, which itself takes power, and fan dissipates the heat to the environment, like for example the room in which the computer is housed, which will heat up, and then you have to run your air conditioner. The air conditioner will have to spend more power and effort to push the heat out. So it has a sort of a cascade effect. Yeah. So all this, well, are serious problems when you try to improve the performance of a single core system. So multi-processor systems, instead of trying to push the performance of a single thread, tries to have more cores which can execute different threads in parallel. Okay, so it exploits thread level parallelism, which was the same that was exploited by hardware multi-threaded processors. Hardware multi-threaded processors and multi-processor systems are quite similar. Okay, from a software perspective, and in many cases from a practicality perspective, it's quite similar. Now, one thing I did not mention is, okay, let me go back here. One point I forgot to mention is the reason for this. OS needs to be SMT aware if we are using simultaneous multi-threading. This was a bit of a problem 15-16 years ago when simultaneous multi-threading was introduced. Okay, slightly more than that, about 17-18 years ago, when SMT was introduced. Operating systems were not SMT aware. Classic example was Windows 98, which was a very popular operating system at that time when I was in college. So if we were using Windows 98, we used to disable SMT or so-called hyperthreading in the BIOS. Any guess what was the reason? Let's say you have a two-core, four-threaded system. So you have two processor cores, but 4 threads. Basically, there are 2 threads per core, which is a very common setup. In fact, that is case for many Intel and AMD processors these days. You typically have 2 threads per core. There are some processors here and there which have 4 threads per core, but that's rather rare. At least most desktop processors have 2 threads per core. So there are 2 real cores, but 4 virtual cores. So when you go to device manager, you will see it as 4 cores rather than 2 cores. Because the operating system more or less sees it as 4 cores. And there are separate registers for each of these so-called cores. Now imagine a scenario where you have 2 very computationally heavy threads and 2 relatively light threads. So a total of 4 threads that are running in the system. If the operating system is SMT unaware, it could end up scheduling the two heavy threads on the same real core. Okay, whereas the two lightweight threads are both scheduled on the other core. And now you are not going to get optimal performance. In fact, these two might end up sort of thrashing each other and giving you a performance which is much less than optimal. Okay, you might be better off having the operating system seeing this as just one core and this as just one core. Then at least the OS will be able to make better use of the cores available. Okay, so if the OS is SMT unaware, it is better to disable the SMT feature, which was possible or which is possible typically from BIOS. Okay, the setting doesn't really exist these days anymore because almost every operating system out there is now SMT aware. So it's okay. Okay, but in the past there used to be a setting in the BIOS where you could disable it. Okay, forgot to mention this part, but now let us go back to what we were discussing. So now we know the motivation for multiprocessor systems. Now there are two main categories of multiprocessor systems. Two main categories. There are a lot of different categories. But the two main categories are loosely coupled and tightly coupled. The differentiation is fairly simple. In loosely coupled multiprocessor systems, the different processors do not share the same memory. There isn't a common RAM. Okay, whereas in tightly coupled systems, all the processors in the system share a common memory at some level. It's typically one of the outermost levels that are shared. But there is memory sharing involved. Whereas in loosely coupled, there is no shared memory. And that would naturally mean that in loosely coupled, each node runs a different OS instance. Whereas here, the various processors are all managed by a single OS instance. Okay, it's one single OS instance that manages all the processors. Whereas here, each processor is managed by a separate OS instance or each node. The reason why I mentioned node is that each node could be a multiprocessor system which is like tightly coupled in itself. Okay, imagine a scenario where you are creating a network of different PCs. Each PC itself is actually a multiprocessor system, tightly coupled, running one single OS instance. But by networking them together, you are sort of creating a bigger computer, but with multiple different OS instances, each node having a separate OS instance. So in such a case, you call them loosely coupled multiprocessor systems, or a more common term to be used is distributed system. Each node runs different OS instances and communicate by passing messages rather than through shared memory. If you have one single shared memory, most of the communication happens through that shared memory. Whereas if you don't have a shared memory, communication between different threads running on different systems will have to be done through message passing, typically over a network. Now, even within loosely coupled, there are two main categories or two different families in a way: computer clusters and computer grids. Clusters and grids. A cluster is relatively closely coupled. So even though it's loosely coupled in the sense that different nodes have different OS instances and different memories which are not shared, they still are relatively closely coupled, at least as compared to computer grids. So they have a centralized job management and scheduling. And the nodes are typically set to perform the same task. Okay, so the nodes essentially do the same task, but typically on different data points, right? Controlled and scheduled by software. So there is typically a centralized, tight control over what each node does. So there is typically a central computer which will distribute the work between or among the different nodes. Okay, and each node sort of acts as a slave to the central computer. And they are typically homogeneous in hardware and software. So typically, all the nodes have more or less identical hardware and software configuration. They typically have the same type of processors, and they typically run the same OS, but different instances. And more often than not, that OS is Linux. Now, typically they are housed in the same building or geography, interconnected using a dedicated network, and they could have shared resources. Like for example, they could have a common printer which is applicable or usable by the entire cluster. And they are typically housed in the same building or same room or same data center. So geographically quite close. And they are connected to each other using a dedicated, typically very high bandwidth, like 10 gigabit kind of network. And often, if you look from outside, it is viewed as one single computer. Classic example for that would be supercomputers. Like we have high performance computing clusters in NUS, right? And you can already see that there is a term cluster associated with it. So supercomputers, computing clusters, etc. are clusters. Then we have grid, which is very loosely coupled. Distributed job management and scheduling. Each node set to perform possibly a different task, but with a common goal in mind. There is a common goal, but each node could be doing different things at different speeds, but eventually contributing to a common goal. Typically heterogeneous in hardware and autonomous in software. Okay, so typically they have different OS instances and different operating systems. Some of them could be running Windows, some could be Mac OS, some could be Linux. There is no real homogeneity in software or hardware. Some of them could be high performance, and each of them could be a cluster in itself. They are geographically dispersed, diverse computers connected through internet. And in some cases, depending on the configuration and depending on the grid, the computers involved might only be using their free cycles. So if you are running simulation on your computer for your own purpose, the computer is not really contributing to the grid. But you can install programs which will make use of those unused cycles to perform computations. A classic example for a grid computing project is SETI at home. Heard of this before? Anyone? It's a project run by UC Berkeley. It has been running for quite long. Even 20 years ago when I was in college, the project was still there. Any guess what it is? Yeah, very good. Search for extraterrestrial intelligence. So basically there are a lot of antennas out there, capturing signals, and these signals need to be processed. A lot of statistical and other tests, etc., to test for non-Gaussianity and stuff like that, which are indicative of some extraterrestrial intelligence. And you can allow your computer to be a part of the grid, in which case your computer's processing power could be used when you are not using it. And crypto mining pools are also to a good extent in the category of grid computers. If you are setting up a mining rig of your own, you will be joining a pool, right? And that pool will have thousands of miners with possibly vastly different hardware and software, all contributing towards a common goal, which is to waste electricity to compute hashes. Okay, now that is loosely coupled multiprocessor systems. Now let us look at tightly coupled multiprocessor systems, where you have processors mounted on the same motherboard or within the same silicon die. So if you buy workstations, you typically have motherboards where you can plug in 2 or 4 or more processors. but they are plugged onto the same motherboard. Or in some other cases, you could have, or in many usual cases, you could have multiple processors within the same silicon die or same package. And they are typically controlled by a single operating system, and they have a single memory, RAM. Each processor executes different programs and work on different data. Each processor usually has one or more levels of private cache. But eventually there could be a higher level cache which is unified, which is common to all the various processors. And memory almost always is common. That's when you call them tightly coupled. And all processors are connected using some kind of a system bus. Okay, it could be one common bus, or it could be a network on chip kind of system, etc. In fact, if you recall, the guest speaker last week had mentioned about some of these stuff. Now, what is a multi-core system? A multi-core system is simply a multi-processor system on a single die or a single package. What is the advantage of multi-core over a standard multi-processor system where there are different processors on the same motherboard? Physical proximity, being on the same piece of silicon, allows the shared circuitry. There is a lot of shared circuitry in a tightly coupled multi-processor system, like a part of the interrupt system, some cache coherent systems, memory controllers, input-output controllers. They are all typically shared between the various cores, and they can all operate at a higher frequency if it is on a single piece of silicon, as opposed to the case where the signals have to travel off chip. Whenever signals travel from one chip to another chip, you are typically looking at a 10x hit in performance. And it's not just performance hit, there is also power consumption. A signal that is sent off chip has to be driven using a very high current. Otherwise, it wouldn't work very fast. The reason is because any external connection is typically big, which means higher capacitance. So to overcome that capacitance, you have to pump in more current, and that will require more energy, more power. Yeah. So from a power perspective too, it's advantageous to have things built on the same die. And some of the multi-core systems are actually not exactly on the same die, but it could be within the same package. Okay, which is not as good as having it on the same die, but much better than having signals traveling off chip. Like some of those AMD, Ryzen Threadripper series, they have multiple dies. The separate die is typically for the shared circuitry, input-output controllers, etc. But yeah, it's still not a single die. Now, in tightly coupled multiprocessor systems, you typically have processors, multiple processors, each with their own private caches, all connected to some kind of a system bus. Yeah. Again, the speaker had mentioned about some of the bus standards that are used in the industry, introduced by ARM in the last lecture. And since multiple processors are involved, if there are multiple processors trying to access common resources at the same time, you need to have arbitration mechanisms. So if two parties try to access the bus at the same time, there needs to be a mechanism whereby one party is allowed access, the other party is made to wait. That is called arbitration. And shared resources need arbitration mechanisms if two processors attempt to use the same resource simultaneously. Like for example, two processors try to access memory at the same time, or an input-output controller at the same time. Then you need arbitration mechanisms. Even for the system bus, depending on the nature of the bus, might require some arbitration. You also need mutual exclusion mechanisms to protect resources which should not be used in a concurrent manner. I highlighted the word concurrent because concurrent is something which is confused with simultaneous. It's not the same thing. Concurrent simply means that they have overlap in access. It doesn't necessarily mean simultaneous access. Okay, imagine a scenario where one processor is reading a mouse and writing the XY coordinate into a memory location or into an array having two elements. Another processor is reading it. Yeah? And let's say the user has moved the mouse. So now the X coordinate and Y coordinate has changed. Let's imagine a scenario where the first processor or the processor which reads the mouse wrote X and there is a slight delay for whatever reason before it writes Y. And if this processor that is reading the coordinates from the memory, if it reads the XY in the meantime, when one of them had been updated, the other one is not updated yet. The processor which reads it will end up reading the X coordinate for the new position and Y coordinate for the old position. Okay, and if the mouse pointer is displayed on the screen, you will feel like the mouse has gone bonkers, right? It will suddenly jump from one place to another. So this is a scenario where you require some kind of a mutual exclusion so that there won't be a concurrent access. So if one processor tries to access it and gets access until it has finished accessing that resource, another processor will not be allowed access. Yeah, so this is called concurrent. It just means that there is overlap in time. It doesn't necessarily mean both the processors are attempting to use that resource at the same time. Okay, this is for memory, but it could also be the case for input-output. Like for example, one processor is using an I2C bus to read from a sensor. So halfway through, another processor should not come in and attempt to use the bus, even if the first processor is not actively using it. It has started using it, it has not finished using it. Okay, so here is where the first processor has started, here is where it finishes. But the access itself is kind of intermittent. But it doesn't mean the second processor can actually try and use the same resource in between. Yeah, so this requires some kind of a mutual exclusion mechanism. Okay, if I can give you a very crude example, let's say if you are going to the toilet, you need to lock the door so that another person will not be able to go in while you are doing your business, right? So you should be able to come out and unlock before another person is allowed access to that resource. So that requires mutual exclusion. And here, in the example that I mentioned, that lock acts as a mutual exclusion, right? So yeah, something similar needs to be there, which is typically done through some kind of what we call an atomic operation. That is atomically writing to a certain location in the memory. And most instruction or all instruction sets provide some kind of an instruction which will allow you to check a memory location and change the memory location in one shot, atomically. And in ARM, one classic example for such an instruction is SWP, swap, which is basically to swap the content of a memory location with a register. So swap is in fact a combination of LDR and STR. The two of them combined into one instruction. So you read a certain memory location and store it in, or load a register with that, or put it into a register and put the content of the register back to that memory location in one single instruction. Okay, which will allow a processor to check a memory location and change a memory location without getting interrupted in between. That is what we call atomically. Okay, each instruction set will come with its share of mechanisms or its instructions which can do something similar to this, which allows mutual exclusion to be implemented. Okay, and these are typically functionalities provided by the operating system. It's an OS that will implement some kind of mutual exclusion mechanisms. And this is one scenario where you will have to write assembly. So these instructions, right, they are typically implemented or they are typically called from within your C code as assembly code. Because you have to guarantee that this will be done as a single instruction. Okay, so if you go into some operating system source code, you can actually see how these mutual exclusion mechanisms are implemented. And deep within, it's always assembly. Because if you try to do something like say A is equal to B, some C is equal to or B is equal to A kind of stuff, in C language, there is no way you can do these two in one shot, right? It will be sequential and that's not allowable for mutual exclusion because there is a possibility that there could be an interruption in between which could mess up things. Okay, let me not go into those details. If you take a course on OS, which many of you have actually done, you know this stuff very well, right? Requirements for mutual exclusion mechanisms and stuff like that. Okay, now let's move on. You also require mechanisms to ensure cache coherence across all levels. There could be multiple levels of cache. Some of them could be private caches which are accessible only by one processor. Some of them could be higher level caches which could be accessible by multiple processors. But you have to ensure cache coherence across all levels. So imagine a scenario where processor 1 modifies a data which is present in its cache. And processor 2 has the same location cached in its own cache, which reads from the location. You could end up with a scenario where the update made by one processor is not visible to the other processor immediately or fast enough. And then the second processor will end up reading the stale data, okay, which essentially means that you have no cache coherence. So ensuring cache coherence across all levels in a multiprocessor system is quite tricky, and that was what most of the test lecture, second part of the test lecture was focused on last week. There are mainly two mechanisms. One is called snooping, the other one is directory based. In bus snooping, the cache controller spies on every transaction on the bus to see if the data inside the cache is affected. So whenever there is any data transaction, the transaction is sort of broadcast to every involved party, or every involved party will listen to what is going on the bus to know whether any relevant data has changed. Any data that is present in its own cache has changed. So that is bus snooping. Then there are directory based mechanisms whereby the transmission in some sense is not multicast or broadcast. Okay, but let's not go into those kind of details. If you want to know more about this, there are graduate level courses where these kind of things are dealt with in a lot more detail. If I recall correctly, there is this new module CG3207, okay, which looks into all this kind of stuff. Okay, there is a new master's program in computer engineering where there is this module on hardware technologies and platforms where many of this kind of stuff are dealt with. Okay, now next topic is symmetric versus heterogeneous multiprocessing. In symmetric multiprocessing, systems have two or more identical cores. Pretty much all desktop class processors, okay, until last year are SMP. It's only recently, a few months back, that desktop systems have sort of transitioned from SMP to heterogeneous. Okay, Intel has just released a few months back a heterogeneous platform. I think only about 3 months ago, can't recall exactly. 3 or 4. Yeah. So what exactly is symmetric multiprocessing? All the cores are identical. So if you are looking at a 4-core processor, all the 4 cores are identical. Okay, they have the exact same microarchitecture, exact same performance, etc. Whereas heterogeneous multiprocessing refers to systems that use more than one kind of processors or cores. So not all processors in a system are identical. They use dissimilar processors or coprocessors. The cores could be totally different ISAs or different microarchitectures but same ISA. So you could have HMP systems, heterogeneous multiprocessor systems, where different processors execute the same ISA but they have different microarchitectures. Or it could be different instruction set architectures altogether. And HMP systems usually incorporate specialized processing abilities to handle particular tasks. Examples would be, many modern systems do have some level of heterogeneity. Like for example, if you look at many of the modern mobile phones, like let's say Apple A16 chip, okay, which came out last month. It has a lot of different types of processors, not just CPUs. And even CPUs are not all the same. Okay, but CPUs all have the same ISA, but there are processors with different ISAs. Okay, apart from CPUs, like there are GPUs, then there are video codecs for video compression and decompression, like H.265, H.264 codecs, hardware specialized for video coding and decoding. Codec means coding, decoding. Cryptography processors, okay, not so common in typical desktop or mobile systems, but very common in enterprise systems where encryption is a very strong focus. You have programmable network processors. Many of your high-end routers, they are able to do stuff like routing, or to be precise, network address translation entirely in hardware. So there is a specialized hardware which can receive a packet, and depending on the port number, IP address, etc., it can change the port number and forward it to the appropriate IP address in your local network, for example. So that's network address translation, which is done by most routers. But higher end routers typically have a hardware level capability to do it, so that it doesn't have to be done by executing a sequence of instructions. The hardware can do it without running a sequence of instructions. So the hardware might have some configuration registers which you can write to configure the hardware appropriately. And once it is configured, once the packet comes, it will be sent to the appropriate party without your software having to go through the packet, inspect the packet and do the forwarding at a software level. Okay, Qualcomm calls it cut-through forwarding. Some of the higher-end routers or even medium-end routers do have this feature, okay, which can give you a higher speed than doing it purely in software. Then we have neural or AI accelerators, which are there in most modern higher performance mobile phones as well as servers. Like for example, Apple has this neural engine, and so has most other system-on-chip manufacturers. So have most other system-on-chip manufacturers like Huawei. They have their own neural processor. Qualcomm has its own version of a neural processor, etc. Then digital signal processors, which are there in pretty much every modern phone to deal with signals such as speech signals, images, etc. And most of these accelerators perform some SIMD kind of processing. They typically make use of data parallelism. And these so-called specialized processors or co-processors which help the main processor do certain type of tasks very efficiently are called co-processors or hardware accelerators. And some of these accelerators might not be ISA based. What do you mean by ISA based? ISA based means you need to run some kind of software to do the computation. Some hardware accelerators might not be ISA based. where you have some configuration registers, you configure the behavior of the hardware appropriately, and then just pump in the data. The hardware does not really look at some instruction memory, fetch instructions and execute. The hardware knows what to do without having a sequence of instructions. Yeah? So those are non-ISA based. But these typically still have something called, a micro program, which is nothing but a sequence of instructions, but at a much lower level than what is visible to the programmer. Yeah, but yeah, basically it could be ISA based or it could be non-ISA based. It could be a micro program based. If it is a micro program, you don't see it from outside. That is, the programmer does not compile a code explicitly for that particular processor. Now, what are the advantages and disadvantages of SMP? Main advantage is binary compatibility. Every processor is the same, which means the same binary can run on any processor. And that makes your system design, task scheduling and performance evaluation a lot simpler. Because the processors are of similar type. So it's easy to quantify or profile the performance of the system. It is also very easy for, I wouldn't say very easy, a lot easier for the operating system to schedule tasks because every processor is the same. So the operating system does not need to worry about which core a particular thread will run on because every core is the same. So if in a 4-core system, the OS simply needs to make a decision on which are the 4 threads that are assigned to the 4 cores. It doesn't matter which thread is assigned to which core. So let's say if I have threads T1, T2, T3, T4 and cores 1, 2, 3, 4. You don't have to worry about which core this thread 1 is assigned to. Any core is okay because all cores are the same. Okay, which is not the case if the processors are dissimilar. Imagine 2 processors are high performance and 2 processors are low performance. Now there is one additional dimension to the optimization problem the scheduler will have to do. Okay, it doesn't just need to figure out which threads to run, it also needs to answer the question of where or which type of processor this particular thread will be run on. One extra dimension added to an already complicated problem. In fact, scheduling problem itself is an NP-hard problem, and now you are adding one more dimension to it. The other advantage, the SMP does not have this complication because all processors are the same. That's what I meant. Now we have fault tolerance. So if you know that one particular core is damaged, and assuming that there is a way to disable that core, the system can still run using the other cores. Because, well, all that we need to do is to make the operating system aware that one of the cores is down. And then the scheduler can assume that that core doesn't exist and schedule the threads available only on the other available cores. Right? And this is possible to be done quite dynamically, assuming you have sufficient hardware and OS level features to do this, but it's possible at least. If a particular core is known to be damaged, the system can still function. The overall throughput, of course, will suffer because one less person to carry the load means the rest of the parties will have to carry a bit heavier load, and if they can't, then the load carrying capacity will go down. But at least it's a graceful degradation in performance rather than an abrupt degradation. Imagine you have a scenario where you have 4 cores which are all dissimilar. So one core cannot perform the function of another core. So if one core is down, then their system is down. Okay, and this kind of graceful degradation is very important in applications where you cannot fix the problem that easily. You don't want to re-engineer or change the system the moment you have a problem. Classic example for this such a scenario would be satellite systems. Okay, you spend millions and millions of dollars or several tens of millions of dollars to send a satellite up there. Okay, and one damage, and there is a higher likelihood of damage up in the space because it is subject to more, harmful radiation, which can cause certain transistors to be permanently on or permanently off, etc. So one processor core being down should not bring down the entire system, right? Should not make the complete system useless. So you would rather have a reduced or degraded performance than having an abrupt, failure in the operation of the system. So that is graceful degradation or fault tolerance. Now, disadvantage is higher cost, higher power for the same performance as compared to HMP. Since all the cores are the same, none of the cores are really specialized. They are jack of all trades, master of none. So they can do anything, but they wouldn't do anything particularly efficiently. So to get a certain performance, you have to have more processors and more power. Power issues can be mitigated to some extent by scaling down voltage and frequency based on the load. So most modern computers have the ability to dynamically change the frequency and voltage depending on the load that is, that the processor has to deal with. So the operating system, depending on its perception of the load of the system, can change the clock frequency of the processor. And some cores which are not very useful possibly because the current system load is not very high, can actually be turned off altogether. And this is typically done by the operating system using some kind of a daemon, like in Linux there is a CPU frick daemon which can do this. So modern processors come with some kind of a table called DVFS table. By reading this table, the operating system knows which are the possible valid configurations and then select one of the valid configurations depending on its perception of the system load. Yeah, so you can read up more about DVFS if you are interested. Now how about HMP? You can get higher performance and lower power consumption for a given performance. Higher performance for a given cost, lower power consumption for a given performance. But problems involved are difficulty in design, difficulty in debugging, difficulty in performance evaluation, difficulty in task scheduling. Okay, so it's not very easy to characterize a system which has a lot of different types of processors. Okay, it's very hard to say, okay, this particular set of computations will require this much amount of time, because that will also depend on which processor does it, what time it does it, etc., etc. So performance characterization becomes more difficult. And as I mentioned earlier, operating system scheduler now has a tougher job to do, because it not only needs to decide which thread to run, it also needs to decide which core the thread will be run on. Especially if the processors are having same instruction set architecture. Otherwise that problem doesn't really arise. Yeah? Now, you might have heard of this framework called OpenCL, which is quite popular. It is an attempt to minimize some of the difficulties associated with heterogeneous systems. So it's a platform where you can write code in such a way that part of the code runs on a host and part of it runs on an accelerator. For example, part of it runs on your CPU, another part of it is offloaded to a GPU or FPGA or those kind of accelerators or DSPs even. So it's a framework for writing programs that execute across heterogeneous platforms consisting of CPUs, GPUs, DSPs, FPGAs, etc. And most vendors, most big companies now support OpenCL. So it's entirely possible to write your code within the OpenCL framework and get it accelerated on an FPGA without really knowing anything about FPGAs. Okay, both Intel and Xilinx, that is now AMD, have their own frameworks or their own compilers for OpenCL for both FPGAs and GPUs. And NVIDIA also supports OpenCL. It's not to be confused with OpenGL. OpenGL is a graphics library which is an API for graphics rendering, whereas OpenCL is for general purpose computing. If you want to know more about OpenCL, there is this module that I teach next semester, CG3207 Lec. Okay, you can take that module. Now, by the way, I'm not sure if you will be allowed to take that module, but you can audit it if you want. Priority will go to master students if I'm not wrong. Okay, now, the problem with heterogeneous platforms is, especially if their ISAs are different, you may need different binaries for different cores. Like, even if you use OpenCL, the binary that is executed on GPU is not the same as the binary that is executed on CPU. It's just that the two of them will run in tandem, hand in hand, to accomplish your goal. But all of this require explicit parallelism. So the parallelism has to be explicitly managed by the programmer. So the programmer needs to say, okay, these things are going to be run in parallel. So that has to be done by the programmer. It doesn't automatically parallelize. And automatic parallelization of a sequential program is considered a holy grail in computing. It's very difficult. It's a very hard problem. By the way, OpenCL is having an alternative which many of you might already know or might have heard of, CUDA. CUDA is a proprietary platform from NVIDIA, which runs only on NVIDIA GPUs, whereas OpenCL is more generic. It runs on a wide variety of platforms. So you can actually have the exact same code used to target platforms like GPUs, FPGAs, etc. But having said that, this OpenCL standard only guarantees software or source code level compatibility. In order to maximize performance, you still need to have a good understanding of which platform it is going to be run on and needs to customize things appropriately. Yeah? So that's why you cannot simply get away using high-level libraries. You can if you don't care about performance. If you care about performance, you have to understand the hardware you are running it on. And then you have limited to no fault tolerance, which we talked about earlier. There could also be data format or NDNS issues. Imagine a scenario where one processor is big endian, and let's say you are storing the data hex ABCD 1, 2, 3, 4. It is stored at locations, let's say 00, 01, 02, and 03. That is one word, right? One word is 4 bytes locations. A little endian processor will store 3, 4 at the location 00 or 03. Little endian 00. It will store the data in this format 3, 4, 1, 2, CD, AB. Now the same data that was written by a little endian processor is read by a big endian processor. The big endian processor will consider this as the most significant byte. So it will read the data as 3, 4, 1, 2, CD, AB, which is a huge mess up, right? So if NDNS is different, you have to swap the bytes within a word explicitly after reading. If the party that is reading and the party that is writing do not follow the same NDNS. Okay, which happens. So there's an easy way to remember this. A little endian processor will store the least significant byte at the lowest memory address. So here, this is a least significant byte that goes to the lowest memory address, which is 00 in a little endian processor. LLL. Okay, so we will continue the discussion next week, where we will talk about some exciting stuff like ARM big little, some stuff about modern system on chips, the level of heterogeneity, etc., etc. Okay, so see you all next week. Have a great long weekend ahead. You have your NUS Wellness Day after tomorrow, so hope you all stay well and happy. And make use of the time to possibly catch up on whatever or whichever you are falling behind in. And if you think you are on track, use that time to relax. This is the last chapter, so by next week's lecture we will be done with all lectures. So the last two lectures will be used for some revision. We will attempt some sample problems from past year's lectures. Yes, sir.
Nothing good.